Right. So here's the second session for today, Wednesday, January. What's that? 7th. All right. Venture College, London, Ontario. Controls 2. Was it CTNL 3020 or CNTL 3020? I'll tell you. Homepage. CNTL 3020 Controls 2. All right. As I said for the other group, here's the content. Here's the course plan. Download it. Just a quick thing here. As far as the course content, we're going to have we're going to have 10 labs, and all 10 labs together are worth 24% of the whole course weight. Then we're going to have one lab test, practical test, for you know what lab test is. That is worth 10% of the whole course. We're going to have 4 squeezes, and all those 4 are going to be worth 18% of the whole course. 2 tests all together worth 24%. So test 1 is worth 12% of the course. Test 2 is worth 12%. Okay. And then the final exam, which is going to be worth 24% of the whole course, and altogether, if you don't believe me, use a calculator. It's going to become, it's going to add to 100%. All right. All the rest you can just see here. Here's weeks and labs against the weeks. We have 2 open lab sessions, and the last 2 weeks are going to designate for the lab tests. Here is the table that shows the week 1 through week 15. All right, and here's the dates. So if you don't know which week we're on, because you might get lost along the way, just look at the date and look at my timetable. Look at my course plan, and look at this table, and you'll be just as found as you were lost before. All right, cool. All the rest, ask if you want. Now, that here, it would be unfair if I just started midway. So we're going to finish that with the other class. When we do the in person, we're just going to bite into the other class here on Monday. I think it's Monday. Okay, now we're going to get the other one. Is that the one? Yes. That's the other cool. Now I have to juggle things. Want to keep your discard. All right. And here is the session right now we're going to do. Ooh, special effects. All right. We're going over the technologies used to transmit power because, fluid power is more or less what these controls are about. It's part of the whole, large part of the course. So we're starting with this. All right. So let's see here. Technologies used to transmit power in modern industry. All right. Ooh, key points. What we're going to talk about. We're going to talk about power transmission technologies, which are mechanical, electrical, pneumatic, hydraulic, and these will be the systems that are used in modern industry right now. We're going to talk about systems comparison. We're going to compare all those systems, and how we're going to discuss how They worked together. Now I see I'm looking at the chat line here. Classes were cancelled yesterday. No, they were not. Nothing was cancelled yesterday. Not for us. We are not the first intake. The first people who never came to school, to our college, they had the orientation session, and I just had to make sure. Yeah, my schedule, my contract starts yesterday. Your classes start yesterday. We had to come and see each other yesterday for the first class, because we're not the first intake. We don't need to see where the cafeteria is. We know where everything is, right? I see. I was told other was. I'm not gonna get into that discussion. Let's not lose time. All right. Okay. All right. We can talk about that later. But we gotta carry on with this course here. All right. Cool. We're going to talk about integrated systems, how they work together. All these, we can use them one by one, and we can use them all together or combination thereof. Electropneumatic, electrohydraulic controls. See, mechanical, electrical, we can combine them together, and we have electromechanical. That's where the term mechatronics comes from. And so on. We're going to look at the control logic versus hardwired logic. Programmable control logic. How the hardwired logic compares to programmable logic, and how things have moved in the industry over the years. And we're going to do a little kind of, if we have time today, do some questions and answers. Okay. Power transmission. Let's see what the power transmission is. Power transmission as the concept of moving energy from where it's produced to where it is used. That's the whole secret of things. All right, and we're going to expand on that. Mechanical power transfer. Definition: transmitting force and motion through solid components without converting energy into another form. Here's one wheel, here's the other wheel. One is larger, one is smaller. They're connected through a belt, transmission belt. Transmission belt, transmitting, transferring, all right, same thing. And the power is mechanical here. It's mechanically coupled and transferred to another, whatever it is, in this case a smaller wheel, and it's still in mechanical form. All right. Key principles of the mechanical power transfer. Direct motion transmission. Use physical contact between components. Example: gears, shafts, belts, to transfer torque and speed. Torque means how hard we're cranking something. With that force, how fast things are spinning. Rigid connections. Mechanical power transfer provides precise control of motion, but can introduce backlash. It can backfire at us, and the complexity of the systems. Do you ever see how Swiss watch is made? It's all mechanical, but it's complex mechanics. Yeah. Energy conservation, highly efficient. The mechanical power transfer is highly efficient over short distances with minimal energy loss compared to fluid or electrical systems. How about load handling? It's ideal for moderate loads and applications requiring accurate speed and torque control. Mechanical power transfer. Maintenance needs, well, requires lubrication and periodic inspection to prevent wear and tear. So it's a little bit involved when it comes to maintenance. Common components with mechanical transfer: shafts, gears, chains, belts, cams, and levers. Mechanical power transfer. Continuing, advantages and disadvantages of mechanical power transfer. Highly efficient over short distances with minimal energy loss, precise control of speed and torque for accurate motion, and simple components, shafts, gears, and belts. That's the advantage. Disadvantages: limited range, not suitable for long-distance power transmission. Can you transmit power mechanically over 10 kilometers? Can you do that electrically? Yes. That kind of thing. Yeah? So mechanical is limited range. Right? Backlash issues. Right? Complex systems due to rigid connections. And maintenance required. So this second slide is sort of like a almost different take on the same things or similar things. Look at the pneumatic power transfer now. By the way, here, FRL. What's FRL? Filter, regulator, lubricator. Okay, let's leave that for now. Pneumatic power transfer. Definition of that is a system that transfers power, power transfer, system that transfers power, through compressed air or inert gas. Inert means non-reactive, stable, or safe. Not going to blow up on you. Again, pneumatic power transfer is a system that transfers power through compressed air or inert gas. Not the hydraulic system yet. It's a pneumatic. Air is involved for the most part. What we're going to be using in our lab will be air. The working medium, what's working in there? Compressed air, stored in tanks and regulated for safe operation. That's what is being used to transfer power. Energy conversion, air pressure converted into linear or rotary motion using actuators, example, cylinders. Actuators are devices that make things move, that cause some sort of action because of the energy that they received. Actuators. Now, with the pneumatic systems, we have fast response. That's an advantage. Ideal for quick, repetitive movements and high cycle tasks. Let's say there is a sorting plant for packages, like UPS or FedEx or something like that. They have huge conveyor belts, and based on the barcodes and whatever other identification means on the packages, those machines can identify where the package is supposed to be pushed as it travels through the conveyor belt, whether it's going to be pushed to travel into another conveyor belt, and so on, and things happening so fast. That's what we need with pneumatics. We don't need high power, but we need speed. We don't need high precision, but we need motion, and we need speed. That's where pneumatic power transfer thrives here. Limitations. Well, lower force capability due to the air compressibility, less precise for mid-stroke position. It can extend far, and it can extend to the other end, and it can do fast. But if you want to precisely bring it somewhere in the middle, then maybe pneumatics is not the right system. Hydraulics, yeah. Electrical, yeah. But not pneumatics. So again, lower force, pneumatics using compressed air, we can't move loads as heavy as we are able to do with hydraulics. But we're talking about pneumatics now. Common components: air compressors, storage tanks, FRL units, filter regulator lubricator units. Oh, there you go. And pneumatic cylinders. Common components. Let's continue with the pneumatic transfer. Gases other than air: nitrogen, carbon dioxide, CO2, natural gas, argon. All right. Primary uses of those. We're doing okay with time. Yes, there is lubricant in the air. So actually, I'm glad you asked that, because I could have forgotten to mention that. In those power transfer systems, we have, well, hoses, we have cylinders, we have pistons. Hoses could be plastic or they could be metallic. Pistons and cylinders are definitely using a lot of metallic components or metallic structure. Compressed air is going to moisturize. So we need to filter the moisture out of it. But no matter what we do, we're going to still have some moisture in there. So lubricating it prevents corrosion. Also, lubricating things within the air systems will seal things better and make things more efficient. So we will seal the gaps. However, in some things like, if it's a mechanic's shop, use compressed air on their power tools, definitely there is some oil lubricant in that air. So I wouldn't use that hose to blow out some dust from some electronics equipment, because there is going to be some lubricant oil is going to spray out with that. If there is like a medical equipment or some kind of specialty equipment, then we're using something that's called the dry air, and sometimes other gases to when some things like pureness of things and maybe non-reactiveness and maybe some other things than air are being used. So yes, there is lubricant in the air. Yeah, like for example here, see, lubricator. It adds a little tiny mist of oil into the air. All right, so nitrogen, other than air gases, used for airspace, high-end industrial applications. It's dry, it's inert, which means non-reactive, and prevents rust. So why can't we just use that? Well, it all comes down to the green stuff, which is the money. It's more expensive than air. Air You don't need reservoir tank for the air because you're swimming in it. You just grab it from the air. Grab the air from the air. Carbon dioxide. Portable tools, hobbyist, high storage density. You can store those in, we used to call them bullets. Those little tanks for pneumatic systems, like pneumatic pistol or maybe airbrush or something like that. Freezing. Oh, okay. A disadvantage is well, it can freeze, and it can be corrosive when wet. All right, because when it freezes, it does moisturize a little bit. It does liquefy. Natural gas, believe it or not. Remote oil rigs, gas sites. It's a free energy source. Advantage of that. Disadvantage, well, it can blow up. So that's kind of a bit of a disadvantage. Argon, it's a gas used for lab environment things, completely non-reactive, but it's expensive. So these are the gases other than air. All right, so we're going to the hydraulic power transfer. What is it? Definition. Hydraulic systems are pressurized, incompressible liquids, typically oil. So you don't need lubrication for that because it is self-lubricating all the time, right? They use incompressible liquids, oil and water is considered to be incompressible. Yes, to some point, if somebody really wants to argue, yes, there's a little tiny bit of compression. Same as, measuring a piece of wire for resistance, that the wire is maybe 3 inches long. Yes, that it does have some resistance, but for our purposes, for the practical purposes, right, that we do use, the resistance is considered to be 0. So same thing with the compressibility of the gases, of the fluids, such as hydraulics, water or oil. It's considered non-compressible or incompressible liquid. So hydraulics use the incompressible liquids to transmit power and generate large forces. Don't confuse that with gaining energy. All right. Key principles of hydraulic power transfers. Working mediums. What they were? Pressurized liquid, usually oil, provides smooth and rigid power transmission. Energy conversion. Hydraulic pumps convert mechanical energy into fluid power with actuators. Actuators being cylinders, motors, turned back into motion. So we have motion connecting into pressure, powering the actuators that convert the energy and back into motion. But we're talking about power transfer from one place to another. And sometimes we can multiply the force while doing the same work. We're using the same energy, but can multiply the force. That's why we can lift a whole car with the power of our own muscles. Using a car jack, using the mechanical advantage of hydraulic power transfer. High power density delivers immense force in compact spaces, ideal for heavy duty applications like this here. Here's a big backhoe. Right? Look, here's a hydraulic cylinder. Here's a hydraulic cylinder. Here's a hydraulic cylinder. Here is a hydraulic cylinder. Okay, we can generate a lot of force. Precision and smooth motion. Liquids do not. Okay, Liquids do not compress, enabling vibration-free and accurate control. We're going to talk about that further. Drawbacks. Risk of leaks. Fire hazards and environmental contamination requires larger power packs and regular maintenance. Common components of the hydraulic power transfer: hydraulic pumps, reservoirs, control valves, directional pressure flow, actuators, cylinders, and motors. What are actuators again? Actuators are things that receive energy and they move. Right. Yeah. Let's just talk about hydraulic pumps because we can. Key principles, because this is an important part of the hydraulic system. Energy transforms, energy conversion. Okay, transforms mechanical power, torque and speed into the fluid power, flow and pressure. Positive displacement. Most hydraulic pumps are positive displacement, meaning they displace a fixed amount of fluid per revolution, creating significant force. Here's a positive displacement. Hydraulic pump. Vacuum creation. Draws fluid from a reservoir into the pump's inlet. Can I find that slide, the other slide, to demonstrate this? Yes, I can. Just gonna bring it. Just gonna bring it here. Look. What we're talking about? Vacuum creation pumps. Look. Here's basically how a car jack works. What do we have here? Oops. I can't have here. I can do this. Yeah, why not? Here's a pump, here's a piston, and here's a piston. This piston is smaller. This piston is bigger. This piston, when it moves down, it moves so much volume of the oil that is present inside the whole system. It displaces so much volume, and it pushes that into the larger tank. Or larger cylinder, or the tank cylinder, creating higher force than the one that we use to push things down. But because this volume here in the smaller cylinder is going to displace that much, then the same volume in the bigger cylinder is going to displace much less. However, with a stronger force up. Vacuum. How is the vacuum created for this type of pump? Here are a couple of something that's called a check valves. Here's a check valve, and there's a check valve. A check valve is just like a diode in hydraulics. Depending on which way you push the medium, let's say oil in this case, the valve is going to open or it's going to close. So, if into this check valve, you push the oil into this here, imagine there's a little ball that is covering that inlet here. You push that ball is going to step aside and let the liquid in. And when the pressure stops, then maybe the spring-loaded action is going to close that valve. so the liquid can go in but can't get out. All right. Now here's another check valve right here. See what's going on here? That when you push it this side, this is going to open, let the oil through. But look, this check valve is positioned this way with reference to the flow, and this check. So if this pump comes down, this check valve is going to block things, and this check valve is going to push things. So it's going to let through. All right. Now when we move up, there's a vacuum being, the negative pressure is being created here in this chamber right here. That's going to pull that check valve to close, but it's going to pull that into open. It's going to grab oil and fill it up and push it again. This is going to check, this is going to open, more is going to get in there. That's how we lift up the car. All right? Vacuum generating hydraulic pumps. Pressure generating mechanical forces or fluid are in the pump's outlet, increasing its pressure to overcome the We'll talk about those later. Mechanically forces the pressure generated pump mechanically forces the fluid out of the pump's outlet, increasing its pressure to overcome the load in the system. Yeah. Okay, we're going to leave it at that for now for this one here. Common types. Gear pumps employ intermeshing gears right here to trap and move the fluid. Yeah. Vane pumps. Do we have vane pumps here? No, we don't. I'll explain this to you. We will for sure. We'll touch on what vane pumps are. Piston pumps. We just saw that one. Okay. Applications: industrial machinery, construction equipment, excavators, loaders, agriculture, everything that requires high power. Vehicle systems, power steering, brakes. You can have hydraulic brakes, or you can have air brakes, but with hydraulics, we're using hydraulic brakes. Check the time. We're good. How else are we going to be? Electrical power transfer. All right. Definition: converting electrical energy into mechanical energy through devices like motors or solenoids. Solenoid is a coil, basically. Key principles: energy conversion. Electrical energy is transferred into mechanical motion using electric motors or actuators. What are actuators again? Things that receive energy and they move. Control precision. Offers highest precision and easiest integration with digital control systems and IoT. Talk about what IoT is. Well, basically it means the Internet of Things, but not in the way that we understand what Internet is. Clean operation. Cleaner than fluid-based systems. No oil leaks. Often more cost-effective than intermittent use. Because electric motor, don't want to use, just don't turn it on. Don't need to change any fluids in there. Don't need to worry about corrosion and all that stuff. Yeah? Don't need to worry about the fluids getting stale. Don't need to worry about changing the oil and things like that. Limitations: lower power to weight ratio compared to hydraulics. Hydraulics, when it comes to power, brute force. Hydraulics take the cake. Less effective for extreme shock loads. Common components: wires, transformers, generators, electric motors. Check the time. Okay, here's where the fun comes. Integration, combining mechanics, electronics, and intelligence in modern communication. Who says that the production line can only consist of pneumatics? It's almost impossible. You're going to get some actuators. You're going to get some triggers. Whichever is best, we're going to use. You can have electrical system triggering the pneumatic arm or piston. Can we make it so it's all done hydraulically or pneumatically? Yes. But why if we can do some parts more efficiently? If it's more efficient or easier for us to trigger a pneumatic piston electrically, then of course we're going to use that. It just makes sense. Plus, you could have electronic systems control the triggers, which in turn are going to trigger the bigger stuff. Let's say what I wrote here. A single machine often contains multiple types of power transfer systems. Whoa. Mechanics, electricity, pneumatics, and hydraulics can be classified collectively as mechatronics. Now, I'm going to stop here for a sec here because that was my thing too. Is anybody from Europe here? I am, and I went through that stage. Do not call it mechatronics, call it mechatronics. Okay, that's all I'm gonna say. I did that. It took me a while to kind of get rid of that habit. All right. Okay, so mechanics, electricity, pneumatics, and hydraulics can be classified collectively as mechatronics when they are integrated into a single automated system. Mechatronics focuses on the synergistic combination of mechanical engineering, electronics, and intelligent computer control to design and operate complex modern machinery. In 1930s, a mechanic was a mechanic and dealt with mechanic things. In 1930s, an electrician was electrician and he was dealing with, or she, with electrical things. Now, things are so mixed up and synchronized with each other that we were required to produce individuals or tradesmen or people who do things in the industry that not just know the electricity, but mechanics as well, and some pneumatics and some hydraulics. Then it makes you a valuable, employable person in today's world. Integration, power transmission is the primary term for principles and concepts, mechanical, electrical, and pneumatics used to transmit and control power through the system. Power transmission, okay. Individually or in specific combinations, these systems can be classified under the following categories: fluid power, automation systems, integrated systems. And you can read later the definitions. We talked about that already. Now, electropneumatic control. Here we have a symbol of a valve. It's one of the simplest valves. We're going to use this type of valve in our lab. There are different versions of this valve, but here's the symbol of that. Now let's take a look at the symbolics of things. What can I tell about this valve? I can say that this is a 3 two-way valve solenoid triggered. All right. Let's take it apart a little bit. This symbol right here, that symbolizes a solenoid. Otherwise, a coil. Otherwise, electromagnet. You provide electricity, you power up the coil energizes, becomes a magnet, pulls something physically towards one way or the other, triggering something that is going to make something move. Solenoid triggered. If there was like a mushroom things, like without these diagonal things, it would be a push button triggered. Right? All right. What can we also tell about this one here? We can see a spring action somewhere here. So that means it does have a resting position when power is off. It's going to, this spring here is going to default this into one of the positions, and it's going to push it away from itself, and it's going to go into this position, so where there's going to be a supply air here. There's an output port here, and here's an exhaust port. For the most part, port 1 is going to be a supply port. And you can see that at the resting position, the supply port is blocked off. Not going anywhere. By the same token, at the same time, the output port of whatever that thing is connected to, probably a cylinder. That chamber of that cylinder is connected to the exhaust port of that, port 3. Right. For the most part, it's going to be port 1 is going to be the input, port 2 is going to be output, and port 3 is going to be the exhaust. Now, what happens if we push the button? But this is not a push button valve. It's a solenoid valve. We do not have to touch that. We just can press a button somewhere 200 feet away. Or we don't even have to do that. We can just have a computer or some sort of a processing unit control that and initiate a pulse that would trigger this. What's going to happen? This here, the whole thing is going to shift all the way that way. So this port here, this air supply port, is going to be connected to this port right here. Alright. And this port here, the exhaust port, we're shifting the whole thing. And that is going to be the exhaust. It's going to be blocked. And this channel is going to be open through the output, so the air is going to travel that way, which means it's going to operate whatever it is, probably a cylinder. 3 two-way valve, solenoid triggered. What else? Normally closed, because at the resting position, the air supply is closed. Where's the 3 coming from? Because it has 3 ports. 1, 2, 3. Where's the 2? Because it can have 2 positions. It can slide this way or it can slide that way. 2 positions. Alright. Electro-pneumatic control. Timing. We're almost there. Fast transmission. Fast signal transmission. Electrical signals travel quickly over long distances, reducing the delays in control systems. So this thing can be electrically triggered. fast signal transmission. Electro-pneumatic. Here's the electrical part of that. Here's the pneumatic part of the system. Flexible system design. Easy integration with controllers, programmable logic controllers, allows for adaptation and automatic solutions. That's what the big trucks use to dump their air tanks. Valves, there we go, yeah. But some of them are automatic. They could be, the triggering could be electrical, or it could be pressure triggered. If there's too much pressure, then the sample of the pressure is being taken by the trigger, and too much, psst, it comes out, right? It sounds like that. Psst. All right. We have the psst, psst systems. All right. Precise control. Solenoid valves and sensors enable accurate actuation, making things move, actuation, and repeatable operations. Here's the electrical type of a trigger here. Trigger makes things move, or not makes things move. Trigger tells the things that move when to move. But it's an electrical device. But electrical device can also be a sensor somewhere on the cylinder. Here we have a cylinder. We have a piston in there. That is being moved by whatever, this way or that way here. And we could have electrical sensor here. There could be a magnet positioned here. And there could be something that's called a reed switch. The reed switch looks like this. That's how it works. And when the magnet comes to that, the reed switch closes, sensing the position. And that thing can be moved. It can be, it could be a slider here or here, depending on. So electrical thing can sense things, and they can send signals to triggers, and they can send signals to the PLCs or any kind of controllers. So that's what we mean by here. Scalability. What does that mean here? Systems can be expanded or modified easily to meet changing production environments. If something needs to be changed, you can way easier implement the change if it just requires rewiring, or even better, just reprogramming. Rather than physically altering the whole production line, running pipes for air and hardwire control and all that stuff. Comparison. Or, no, not yet. Electro-pneumatic control. Checking time. Almost there. Real-world applications. All right, industrial automation. Assembly lines used for controlling actuators, robotic arms, and so electro-pneumatic control. Used for controlling actuators and robotic arms in automotive and electronics manufacturing. Again, what are actuators? Again, actuators are things or devices that receive energy. When they receive energy, they move. Turn energy into motion. Packaging machines. That usually would be the hydraulic, not hydraulic, would be pneumatic systems. We'll talk about more later. Enables precise and fast movement for sealing, cutting, and sorting. Right? Material handling, conveyor systems, electro-pneumatic valves control air cylinders for delivering packages, pick up and place robots. Process control, food, beverage industry, automated filling, capping systems, relying on pneumatic valves. Pharmaceutical production ensures clean control and actuation for closing and packaging. Transportation, railway systems, automated doors, and there's no end to this song here. And all that can move fast, can move repetitively, and can work forever without, it doesn't need a lunch break, it doesn't need to sleep. Electropneumatic control sensors. You see here, here's a cylinder, here's a piston inside, and here is a position sensor. You can slide that, you can position it anywhere, and you can adjust where that something moves to that point. Send a signal that is going to tell the microprocessor that signal was received from this particular spot, from this, and then it's going, the other thing is going to know what to do with it or ignore it. All right, we gotta finish. We gotta stop right here. This was, this whole thing was designed to be a 2-hour lecture, so we're going to bite into the next week a little bit. Yeah. So the next in-person class we're going to continue from here. And I'm going to post this on YouTube, so you can, well, you already did this, and you're going to see the lecture notes posted on FOL. And I'm going to ask you to watch the other first part of the other presentation, so we are synchronized with the schedule. It's just the first week that we're just kind of like, we have to cover what we have to cover. When will be available? The notes are going to be available within about 15-20 minutes from now. It's going to take me a little bit longer to process the videos, but they will also be posted tonight. All right. Thank you, guys and gals, ladies and gentlemen. You are wonderful, but not as wonderful as me. I'll see you when I see you. I have to find the stop button here again. Bye.